Hi. So this talk will be different. It'll be fun. A lot of pictures. Won't be boring talk. And you will learn about FPGA. You will know more about FPGA than any other person in this conference probably. So I'm Jatin Kataria. I'm the principal scientist at Red Balloon Security. And I'll be talking about defeating Cisco Trust Anchor. So you probably know this device, right? Like this is ASR 1001X, top of the line from Cisco. And our main objective from DARPA was to run modified firmware on this system, right? And we have been doing research for the last 10 years on Cisco routers. You can read papers in 2011 where we defeated around 300 different thousand images where we built a unique exploit for Cisco devices. So we thought it'll be really easy to do this, and but turned out we found about Cisco proprietary secure boot, which was deployed in 2013 by Cisco to basically prevent people like us to run code on it. So we took it as a challenge, and during the course of this research, we reported a vulnerability named Angry Cat. It's basically 3 angry cats floating in space. That's actually drawn by our graphic designer. And we reported the vulnerability was about like Cisco Trust Anchor, which is the core root of trust for their secure boot. But before I explain this, like how we achieve this and what it is about, I want to talk about the impact of this vulnerability. So when we reported this, we thought we are only affecting one series of Cisco routers, which would be ASR 1000 series. But it turned out that we affected these, keep on going. It's around 133 products we affected. And recently they added 12 more products, so around 145. So, and I want to also focus on this. Recently noticed that they have actually added this also. These are Cisco ASA and Firepower, which is their security appliances. So we affected their core IP. And the novel technique which we are talking about here doesn't just affect routing infrastructure, but it also affects weapon systems, ADAS systems in automotive, medical, utilities, wherever FPGAs are used. So in order to explain what we affected, I want to explain what is inside an ASR 1001X. So as you can see here, the A represents the SPI flashes, which contains the firmware. As you guys know, which is Cisco iOS XE, the bootloader which loads this iOS XE. So that's in those 2 flashes, which is marked as A. Then B is where the FPGA bitstream is stored. And I will explain what is a bitstream in my future slides. And then C is the route processor. When you go into the console of a Cisco router, all the terminals coming in, that's basically what C does. It's an Intel Xeon processor. And D is the south bridge. E is the FPGA itself. Next is I want to do some software analysis, like how the system boots. Cisco started since 2013 using UEFI interface as a bootloader. And I don't have to explain you Raman because you guys are networking gurus. So what Cisco did was they implemented pre-Raman, which is a manager for Raman itself. And what it does is that it performs and validates the upgrade of the bootloader. It also raises any concerns. It raises an error if the upgrade integrity is compromised. The next is Raman itself, which is implemented as a DXE module in the UEFI interface. And what it does is that it validates the signature check of the Linux of the iOS XE. And it also has a privilege mode, which you probably don't know about. And they disable it by default. And you can enable it if you mess up with the SPI, which allows you to do memory introspection during that stage. And then what Raman does is that it, after validating the check on Linux, it passes the control to Linux, and then it boots iOS-D. So this is basically from last 20 years, Cisco has been running this iOS stack, which is their core networking stack. What they did was they took that stack, made it into a Linux process, ran it as a daemon, and it's almost the same code. And They run it, and they also manage it using a proprietary process manager. So if you crash this iOS, this whole system boots, even though it's running as a process. So, and this comprises of iOS XE, as you guys know. So after doing the analysis, we found that there are no hashes in the image. There are no certs available. So it should be really easy to modify the UEFI and complete the project. And that's what we did. We disabled some checks in pre-ROM on stage and booted the firmware. Everything worked. But wait, it actually reset. So the reset happened exactly after 100 seconds. And there were multiple theories where we were like, why is this happening? Whether we messed up the SPI flash, maybe there is some other checks which we don't know about. And what it does is that it tries to do the reboot 3 times, but then it falls over the ROM on console. So we started the hypothesis for this 100 seconds. These days, x86 come up with a lot of mitigations. So we started thinking about, OK, let's try what kind of mitigations are enabled in this system. So we looked at the VMM layer, which is the ring -1 layer. We saw that it was already disabled. As we had 100 seconds, so Cisco allowed us to give 100 seconds, which made us try different things with the firmware. So we disabled the watchdog timers. That was not it. Then there is the SMM mode inside the Intel x86, which is the ring -2.5. And we disabled that because we had 100 seconds to do this, and still it was rebooting. So at this point, we thought we should probably do some EM analysis. And this is our setup for the EM analysis. This is actually a self-made robot which goes over different places. And you can attach a near-field probe and get readings of what is going on. And this is what we found. We found that there is some readings on the Bitstream SPI flash, which was the B in the image. Then the FPGA boots up, as you can see, and then the circuitry comes up. So this gave an idea of maybe the FPGA is coming up first, but we thought it was only being used for crypto computations. There's some other guy which we don't know about, which is doing all this resets. And we also, the route processor itself boots using those 2 SPI flashes. The FPGA also boot using the SPI flash, the other SPI flash. So what we did was we sniffed the SPI bus. What is going on? What traffic is there? And we found there was the microcode for the Intel x86. We also found that there were interrupt handlers, which are usually, back in the day, if how your keyboard works, how your mouse works, so those kind of interrupt handlers. And then there was BIOS also, which usually exists in E1000 range. So, after doing all this analysis, we started maybe looking into pre-ROM on. We thought that maybe it's the pre-ROM on which is doing the validity of the upgrade also. Maybe that's how it figures out, it's some magic that, we have modified the firmware. So we found this range, which is the FVD, that red box. And this is where in Intel x86, if you put any external device, if you attach any external device through the serial quad interface, which is the SPI interface to x86, this is where the memory is mapped usually. And we saw that there are some checks being done. So we knew that some external entity is there which is doing this. And just to be sure about this, because the stack is so big to reverse engineer, we wrote a custom serial driver, and we hijacked the first instruction which the route processor runs. And even then, the reset was happening. So we knew, some external entity exists. I don't know who it is. And our, hunch was that it is the Xilinx FPGA. So this was our assumption. As soon as you turn on your router, right, this is what happens. The FPGA comes in, reads program itself, and then it provides the microloader to pre-ROM on stage, which is basically the x86 stage. And then the pre-ROM on boots the ROM on boots the Linux OS, and then Linux OS boots the IOST. So if you actually own FPGA, then you own the whole system. And basically, you can control different parts. You can sniff traffic. You can just live there, and no one will know about it. But in order to validate this theory, we wanted to see, where is the reset pin? We wanted to, before we start doing FPGA reversing, we wanted to validate that this is it. But these routers cost a lot, even on sale. It's $11,000 on sale. So at this point, we thought, we have to, sacrifice our $10,000 and find the reset pin. And it's a BGA chip. So we had an intern who spent a week mapping every pin out, and we found the reset pin. At this point, we knew that RTL reconstruction is hard. RTL is basically the registers transfer language through which FPGAs are programmed. It's hard, so we wanted to adjust the FPGA theory before we invest more time in it. So what can you do? How about just keep the reset pin high all the time? What could go wrong, right? This is what I thought, what could go wrong? So I'm not a hardware person, I'm a systems person, so I went to my colleague, he's my teammate. I usually go to Ong or Rick for my hardware problems, and I said, I want to keep this pin high, what should I do? And he said, why don't you put a 10K resistor and keep the pin high? What could, this will work. And then goes the other $10,000. So basically, we are at this point, total cost of $20,000 gone, and it's around $1 per ohm. That's how much it was. So one of our colleagues basically said, hey, I found this patent where Cisco is actually saying that they could use this FPGA, they could connect this FPGA using the LPC bus, which is basically the high-speed bus connected to the South Bridge, and we can make the FPGA master of the SPI bus. We can validate what's going on. This is their theory, right? This is in 2012. And they said that they can also control different things, like your console. They can control the fans in the router. They can control different quantum processors, which are doing packet switching. So FPGA is actually a single point of failure for them. And also, I forgot one thing. Each time the FPGA finds out, there is something wrong in the bootloader, it makes a huge fan noise. And finally, it made sense why it was making huge noise, because the FPGA is controlling the fan also. So this solidified our theory. And at that point, we thought, FPGA reversing is too complex. We left the project in mid-2017, and we went for our lives and enjoying it. But then we came back in 2018, and I was like, I'm down $20,000. Give me more money to buy more routers, and I can definitely hack FPGAs. But being a systems person, what is FPGA? I have no idea. I'm not a hardware guy. And this is what basically represents an FPGA, right? It is an ICU, which includes the benefits of both software and hardware. You can add computations like hardware, and you can reconfigure it like software. But really, how does it work? So a programmer specifies a hardware circuit by using this software language, which is the hardware description language. Then the vendor toolchain maps it, it compiles it, synthesizes it, and then creates routing between hardware elements. And that routing, you can also do it by the developer can also do it, or the vendor toolchain can do it. And then it generates this hardware information about truth tables, the memory, what does the memory contain, multiplexers, how the routing should do. Think about all the switching matrix is generated. And then it's encoded into a binary, and that's what's called configuration bitstream. So the FPGA reads this. As soon as the FPGA boots, there is a logic which reads this configuration bitstream from anywhere and programs itself and tells what it is going to do now. And then there are different types of FPGA. So most in the industry, and for Cisco, we are talking about SRAM-based FPGA. What it means is that, as soon as the power goes away, SRAM means it's volatile, right? So as soon as the power goes away, FPGA has to again read the bitstream from some flash to program itself. Then there is the flash-based FPGA, where the configuration bitstream is inside the die itself. So it is quick, there is less power consumption, and it boots itself really quickly. And then the antifuse, which defeats the purpose of the FPGA because you cannot program it once you have configured it. But really, what is still an FPGA? I don't understand that. So you can think of FPGA as this. It's basically it's a combination of different blocks. Here, IOB, CLB, BRAM, and all this jargon, which I'll be explaining later on. But really, FPGA is just y is equal to fx. If you think about it, this is a map. And you don't have to worry about anything. And if you want to defeat FPGA, you only have to worry about y or x. Why to worry about f? And that's the logic behind our novel technique, where we cared about if we only change Y, if I can change that reset pin to be 1 instead of 0, I win. And usually hackers are lazy, and that's what we go for. And to give you an idea of like what is IOB, it's basically something which drives a pin 1 or 0. So you can think like that. And then what is IOI? This you can think of it like a routing matrix. You know, you are networking gurus. So think of it like this basically explains you where the signal has to go from one component in the FPGA to another one. So it's really, there is an exercise which will come later, but I/O interface is very important to do that exercise. And then the complex logic block. This is the Boolean. This is the element which implement different Boolean functions or act as a storage. So you know, it consists of different slices, and each slice has flip-flop, lookup table, mux, gates. So think of like lookup table and mux as your switching matrix, which explains you where the bits have to go. So think of it like a hash table. And then flip-flop, you know, act as a storage devices, and then gates does and or. And then again, the switch matrix on the left-hand side is basically how it talks to other elements in the FPGA die. And to give you an idea of like what the complexity of the CLB is, this is what we are talking about, right? Like this is one of the, just one element in the FPGA of which explains why a hacker wouldn't like to go after this. So let's reverse the FPGA bitstream, right? There has been some work done back in the day, like JBits is something which Xilinx released in 1999 about like, you know, where you can change the bitstream after where you don't need the source code, and you can just directly modify the binary. Then Bill is something which, you know, this guy basically said, you know, unless you have a netlist, which is, think of it like when you compile a program, the intermediate stage is what's called netlist in FPGA. Unless you have a netlist and you have a binary, only then you can make these changes. So our research actually, you know, there has been certain paper where they basically said that that's not true. And then Bitman, I haven't looked into this much, but this guy is basically saying that I can move the logic around without having the source code. But again, all of them are trying to do some CLB. What we are trying to do is just change Y in Y equal to Fx. So CLB, as we did some analysis and we found out that as the FPGA complexity increases, the CLB counts keep on increasing. And again, hackers are lazy, so why to go about that? But the I/O count remains same. So if I figure out like how to change the I/O, then I have uniquely, you know, compromised the whole family of the FPGA, and that's what we are going for. So for Cisco, they use Spartan 6 family of Xilinx, and as you can see, the graph keeps on increasing with the complexity of the family of the devices in the family keeps on increasing. So the max one is 147,000 device, you know, CLB cells, but the I/O count remained almost same. So in order to explain like what it is, so what we did was we took the SHA-256, or I think 512 computation, and we compiled it. And this represents only a small part of that computation. Like look at the routing which is happening here, right? Like it's just crazy. Like so, and this is another way to look at the FPGA bitstream. So what I'm trying to represent is the bitmap of the bitstream. It's the same bitstream which we saw the complex routing for. So the top part represents the CLB, where most of the logic of the CLB exists. And then the IOB are down, you know, like as you can see on the red. And then we made one single change, a small change in the number of rounds of the SHA, and look at how the bitstream changed. But the IO remained the same. And if you diff the two, it basically proves the fact that CLB is too complex. It cannot be uniquely modified. And if we modify the IOB properly, we can actually uniquely apply it to different devices and different families, which basically you know, helped us to go after it. So there are a few modification scenarios we are looking for. We want to change the pin to 0. We want to change the output pin to 0. We want to change the output pin to 1. We want to make output to input, and then again, input to 0, input to 1. And make, again, input to output. So these are the modification scenarios we are going for. So here I want to like stress on the fact that what vendors have been doing, or I don't want to just say Cisco, I mean it's everywhere, where how they're applying the model of security is through obscurity. And as we have seen here is that even though RTL reconstruction is hard, but changing I/O is not. And again, it's y is equal to fx. So how do you go about bitstream reversing? So when we do any kind of analysis on a firmware, for your programs or any kind of software, what we go about is you have to unpack it because the software has been compiled in some way. If you unpack it, analyze it, modify it, and repack it somehow, you can reach the same thing with different functionality. So also, like what vendors did was they thought like applying encryption is enough. Like they're just going for confidentiality, and if you talk to them, what if your bitstream is encrypted? How would you modify it then? But there has been so much research done on where they have done side channel analysis because they usually use symmetric encryption, and you can actually do power analysis to figure out what are the AES keys. And if you want to look more into it, check out Riskier Papers. They do a lot of work on it. We have done fault injection, which is called BATFET. That's how we defeated Cisco Secure Boot on a phone, 7941, which is probably in your on your office desks. So you can do fault injections where you can skip the check after, like if there is any problem in the encryption. And people have done photon emission analysis. I don't even know much about it, so. So this was the development board which we used for our research. This is using a device which is LX45T. That's what Cisco used. And we found a dev board for doing our online analysis. So let's go about like how do you do the unpack of FPGA bitstream. All you have to do is just read that document, and you will figure it out. So to go about it, so to do an unpack, the FPGA bitstream, as I said, like FPGA has special logic to read its own configuration. And it all starts with sync word. It's a special magic marker which tells the FPGA hardware logic that this is where my configuration starts. And then the ID code, which explains what kind of device it is in that family. Then the CTL, which basically tells whether the FPGA needs to use the decryption logic in the hardware to decrypt the bitstream. And then it finds the command, which basically tells when to configure itself. And the FDRI register is the one which tells where the bitstream is going to start. And then desync is another magic marker which tells I'm done configuring it. But here a cool thing is that if you, again, after desync, it's really cool, like if you know about hardware trojans. So here we had an idea where, even if the vendor has put in the perfect bitstream and there is some space left, usually because these SPIs are 4 megs or 8 megs, you can add another sync word afterwards, and FPGA will reconfigure it himself. So it will forget the configuration from back, and you can redo the whole FPGA after using that sync word. So that's another problem in it. That's why you need the confidentiality and authentication. Then you analyze it. So there are different types of frames. Each FPGA can be thought of as like the bitstream can be thought of as like frames, like basically arrays of things. And each array is, in this case, is 130 bytes. There is a type 0 frame, which configures the CLB. Then the type 1, which explains the memory part of it, the initialization portions. Think of like if FPGA is doing SHA-256 computations, then all the initial constants of the SHA-256 are kept in DRAM. And then the I/O interface, which we care about. So these are some nitty-gritty details of like this specific FPGA, which Cisco uses. And this is what is cool about is that like you can think of it like a 2D array, a 2D matrix. And each matrix has a row and a column and a major and a minor. I think if I show you this thing, right? So this is a really cool UI. You can actually access it. We are hosting it, and you can put in any configuration bitstream in our to our tool, which we have, which is on GitHub, and there will be a link shown. And you can analyze the bitstream if it's from Spartan 6, and then you can visually see how the bitstream is laid out, which column, which major, which minor represents which bits. It's really cool. So here, as you can see, This is a small example, which I have it on the table, and it basically turns on 4 lights. And you can exactly see in which row the bitstream has, which row the vendor tool has put in, or vendor tool has utilized the resources. So it's basically multiple units of different resources, and they can choose whichever element you want to use. And as you can see, we exactly specify which of the cells have been used properly. And you can actually change it. You can change the switching routing. You can basically make an FPGA do, instead of talking to a different pin or a different SHA algorithm, you can change it to do even MD5, because it's all about changing. All the Boolean functions are here, so you can implement it. But again, we are focused on I/O changes. And this is the representation of Cisco FPGA implementation. So as you can see, they are using most of the resources. All the gray ones are unused resources, so you can use them for your own, for your own functions. So you can put in hardware trojans, which no one will ever figure it out. And I want to actually show you this tool. So, one second. So if you go to this, so if you go to this website, and it's called balloonrouge.github.io. And there's this tool, which we have open sourced also, and you can actually you can supply a bitstream to it, and you can specify which pin to turn it off, which pin to turn it on, and it generates a JSON file, which you can load it. One second. So if you go here, this is representing this Mojo board, which has LX9 bits. It's a device called LX9, and I have basically built a circuit which turns on 4 lights. And you can actually go, it has parsed the whole thing, and you can see here the whole bitstream. And it specifies which model it is. And this is the FDRI, which explains how to configure different hardware elements. And you can go in and see how different resources are actually used. And I'm pretty sure whichever routers you're using, they probably have an FPGA. And you can take that bitstream, put it in our tool. You can add, like if they're using Altera or something, we haven't added much support for it, but the module has been designed in a way, it's a very modular way. You can use most of the parsers we have written. And you can basically analyze what your routers are actually doing, what components it contains. And it also explains, like if I go here, what it is trying to use. So pretty cool tool. Then going back. Oh, actually, I want to also show what it can do. So here, as you can see, there are 4 pins right now, right? And I'm going to just take the bitstream, which is a binary bitstream, which you can dump it from your router. I'm going to disable one of the pin. I'm going to make one pin from 1 to 0. So here, if you see, I'm just telling the P123, which is the pin name, to turn it off. And without changing any source code, all done through bitstream. And we are all victim of software. It's going to load it, and no software required. Just analyze the whole thing, turn it off. Now, I would highly recommend you guys to check out this repo. It's called Bal Xilinx. all this code has been open sourced. We want people to like contribute to it. Please check it out. There are examples to work with this specific device. If you want to do some FPGA analysis, you want to learn about FPGA, Mojo is the right board to go about it because it exposes all the pins. Because in the end, FPGA is just about pins, which takes input and output. And as we can see here, oops. I think my camera froze. Well, while this is happening, we can go ahead and do other things. Yeah. Camera first. 1 second. Well, you can see there are 3 lights on. I'm no sacrifice to demo gods was not happened, but anyhow. So there is an algorithm about like how you can actually figure out which pin represents which bits represent which pin, and you don't have to worry about the algorithm because it has been written in that GitHub repo. Again, all you have to do is like write the unpack logic for the Altera, and you should be able to use most of the things which we have developed. How you modify it, again, there is a modifier in that GitHub repo. It's basically figuring out the CRC during repack. So what Xilinx does is that it uses a weird algorithm for CRC, which is a 22-bit CRC. It's usually, they developed it not for security, but for single event upset. So while configuring your FPGAs, there might be some problems in the electrical circuit, and it can cause issues. It skips a bunch of registers, very proprietary. And then what it does is that it raises this pin high. So you cannot, during our analysis of Cisco, we had to actually attach to it because it took us some time to figure out that register, that algorithm. And then if it is encrypted, again, doing the side channel analysis to figure out the AES keys, and then you can use that AES key to encrypt it again. There's also this register called CRC bypass. So if you configure the FPGA to bypass the CRC, you can also skip the CRC. And this was the demo which worked, but not the camera. Then the idea was that we have developed this technique where we can automatically extract the FPGA, analyze it, and then modify it. Now we wanted to apply this logic to Cisco routers, right? And the idea was pawn the pin, pawn the ASR. But again, the LX45T has 296 pins. And how it works is that this SPI chip, which is attached to the board, there is no way to program it. And you have to take it off, program it again, take it, put it back on. So it takes around 15 to 20 minutes. We timed it. So Rick, the second author in this, came out with the cool idea of like JTAG chain. So in Cisco routers, you have JTAG in there, and they left it out. So you can use the JTAG chain to figure out which pins are enabled when the fan noise goes up. Because when the FPGA figures out like the hash of the firmware has been modified, the fan noise goes up. And that was our cutting point to figure out which pins modified the state using JTAG scan chain. So we found 10 pins, but again, it's 10 into 15 or 20, let's say, 200 minutes. Who's going to spend that much time? So we had everything to create these bitstream modifications. We have written the automation framework, but I need an automation framework to test this thing. So I moved to my intern, my automated bitstream extraction and testing framework, Brian. So in worst case, what will happen is that if these 10 pins doesn't work, he has to sit down for 296 pins. And then finally, we pawned the ASR. We pawned the pin and we pawned the ASR. So the logic worked. We were able to disable it by just changing y in y equal to fx. But again, now the question is, if you go to Cisco, we have to figure out how to do it remotely. And we started doing more analysis. we found out that you can actually modify the bitstream of the FPGA through the Linux kernel in the iOS XE. There's a CPLD driver which allows the upgrade of the FPGA. This is the first problem here, right? Like why in the secure boot chain, why the trust anchor is being modified through something which is high above the chain in the secure boot chain. So it was pretty easy. They had a driver called quack.ko, pretty cool name. We hijacked that quack.ko. We updated, basically reverse engineered the driver. And all you have to do was take this, install this modified driver, and it will update the FPGA with the modified bitstream, which will disable the check. But we needed root to do insmod on the Linux kernel, which is how you, load drivers. So we started writing protocol fuzzers. Like this is a 20-year-old code which they have taken and made it as a process and running on this Linux kernel. So, we probably like fuzzed it for a month, and we found some crashes, but none of them were, like allowing us to get root. Then James, one of the team members, basically said, Cisco has implemented most of the analysis, the management in Lua. So he said, Lua is easy. I can hack it. He went ahead, got command injection in FTP credentials, and that's the CVE number. And he also said it lacks CSRF protections. That's the CV number for that. And we were able to get root. And once you had root, you can upload the modified driver, which will modify the FPGA bitstream, and we will win. And let me show you. I didn't bring the router with me. Usually I bring the router. But each time you do this update, there is no way. There is like a person has to go in and actually take out the chip, update with the real, the original bitstream, and then apply it. So I've lost $10,000 more during the demo, so not bring it. This is the demo. So the idea here is that we will use one of the vulnerabilities, which get us the root. So this is actually pretty important. So when a router boots here, as you can see, it says the system integrity status. This represents that, like this is what FPGA is telling the system that everything is good, right? And it boots up then. Does the whole boot chain which we talked about, boots the Linux, boots the iOS. This is the iOS. And now we're going to attack, use the command injection vulnerability to get root on the system. And again, like people have been talking about, like a lot of reporters say, like you need root to do this. But the idea is that there are so many. If you just go to like their website, you can see like there are multiple ways to get root, and that's not the idea what we are proposing. The core problem here is that the root of trust is mutable, and it should not be like that. So here we have updated the bitstream now, and now we're going to update the ROM on. So the bitstream, the FPGA was validating the ROM on. If I have updated the FPGA, disabled the check, and now updating the ROM on, I should be able to boot the router. So it's updating the whole ROM on. And then if you reboot the system, after 100 seconds, so as you can see, I could remove this, right, because I control the FPGA, the firmware now. But just to explain like what we have done, FPGA has reported that something is bad, but we have basically disabled that reset pin. So even though the FPGA is sending the reset pin signal, that is disabled, right? So it wouldn't reset the system. And it goes ahead, and the modified ROM on boots in, and upgrading the firmware, and ta-da, that's our mic over there. So now we have modified firmware running, and let's get back. So what was the final cost, right? $10,000 for the sacrifice, $10,000 to test the idea whether the FPGA is doing it or not, $10,000 the automated extraction, the Brian framework costed us $10,000 too. And then during the demo, $10,000 during demo, so it's a sacrifice to demo gods. But what about mitigation, right? The only mitigation, once you apply this patch, the only way is someone has to go there, desolder the chip, and basically prefix the bitstream. So Cisco since then has released the patch. I've looked into it, and what they're doing is that they are not allowing the FPGA upgrade to happen anymore. They keep the SPI. In order to upgrade the SPI, you have to select the SPI, and they keep the SPI line low, which is actually pretty cool. But there are other ways to do it, which we are going to do research in. But the core problem here still exists, right? It's still a mutable root of trust. It's supposed to be configurable. It's an FPGA. And that's not how secure boot chain is created. It should be focused on an immutable thing. What the question for the vendor is that if it has been deployed in the wild, right, what we need is a tool for detection. Just encrypted the bitstream would not work because side channel defeat that, those kind of side channel attacks can be used to defeat those measures. Adding authentication in hardware actually improves the security, but the side channel attacks are still possible. But in the end, we are down $40,000, actually 50. And in future, we want to look into hardware trojans, which I talked about. We want to see if we can use Fontana, which is basically a way to transmit information if these things exist in some air gap facility. And FPGA also uses compression, which we haven't been able to figure out, but gladly Cisco used the uncompressed bitstream. Again, this is where the module is, which we have open sourced the whole code. And I want to say thanks to Rick, Joey, James, my automated framework, Brian, the intern, Alex for building that really cool UI tool, and Atreides partner who were with us during the start of this project. And just to explain you what it feels like to lose $50,000, that's basically $50,000 to the cat goddess. Any questions? That's it.